Hi friends, this is Syed Reshma Sharif. Today I am going to discuss about topic that is law of junction in electronic devices and circuits. In previously what we discussed about P and N junction diode and how the formation of diode as well as how the concentration in both the P type and N type. Now here this is little different, that is law of junction. What is the law which is present at the junction side? Let us discuss. Okay, if the whole this all this topic comes under the depletion layer, that is depletion layer or depletion region. Okay, all this entire law of junction we discussed between depletion layer or depletion region. Here the whole concentration at the edges of depletion layer are PP and PN for P and N type materials. Here we are going to use P and N type materials, isn't it? So PP and PN, these both are concentration of holes at the edges of depletion layer. Okay ma? PP and PN are the concentration of holes in the edges of depletion region. In which diode? That is in P and N type materials. Okay. If the barrier potential across this depletion layer is VB. Barrier potential or barrier voltage. Okay, the barrier potential here is nothing but VB. Okay, then PP, concentration of holes at P type material, that is nothing but Pn e power of VB by Vt. This is of equation 1. Okay, this is across P type material. Okay, this is the Boltzmann relation of kinetic gas theory. This entire equation 1 is nothing but a relation of Boltzmann kinetic gas theory. Remember this one. This is Boltzmann relation. For what? Kinetic gas theory. Kinetic gas theory. This is the relation for Boltzmann relation for kinetic gas theory. Remember this one. All enter this law of junction. We are going to discuss about P type and N type materials, where P type and N type materials, the whole concentration are PP and PN for P and N type materials. The barrier potential for this depletion layer is VB and PP is equal to Pn e to the power of VB by Vt. It is the Boltzmann relation for kinetic gas theory. Okay. Now for open circuit PN junction diode, this is about a closed circuit. Now for open circuit PN junction, open circuit PN junction is nothing but PP is equal to PP naught for open circuit. So I mentioned P naught, okay, or PO. Then PN for N type material, that is nothing but PNO. Now VB is here, it becomes VB is equal to V naught. Okay, V naught is nothing but is contact potential. Okay, V naught is contact potential. Now substituting PP is equal to P naught, Pn is equal to N naught, and Vb is equal to N V naught in this equation 1. Now what we will get? Then substituting this equation in equation 1, what we will get? We will get PP naught is equal to, here in this place Pn plus I am putting Pn naught, okay, Pn naught e to the power of Vb plus we are going to put V naught by Vt, okay. This is equation number 2, okay. Now after substituting, what we will get? We will get Pp naught is equal to P N naught e to the power of V naught by Vt, okay. Now consider a forward bias junction with an applied voltage. Consider a forward bias junction with an applied voltage V. Then the barrier voltage will be Vb. Barrier voltage, okay, is decreased from its equilibrium value V naught by the amount of V. See here carefully, listen here carefully. Vb, that is barrier voltage, Vb is decreased, Vb is decreased from its equilibrium value V naught by the amount of V, or Vb is equal to V naught minus V. See here, this barrier voltage or barrier potential, this is decreased for forward bias junction. For forward bias junction, this applied voltage Vb is decreased from its equilibrium value V naught by the amount of V. So Vb is equal to V naught minus V. V naught is nothing but a decreased voltage or equilibrium value V naught, okay. V is nothing but applied voltage. The whole concentration throughout the P region contains an equal to thermal equilibrium value, or Pp is equal to Pp naught. Okay, this is a whole concentration through P region. This is for whole concentration to P region. Okay, and which is equal to thermal equilibrium, that is Pp is equal to Pp naught. The whole concentration varies with the distance into N side. Which varies? Whole concentration. Whole concentration varies with distance into N side. Okay, at the edge of depletion region or depletion area, the distance from junction is x is equal to 0. Okay, Therefore, Pn is equal to Pn0. For this case, Boltzmann relation is P0 is equal to Pn0 Pn of 0 or e to the power of V0 minus V by Vt. For which case? For forward bias junction, here Vb is equal to V0 minus V, that equilibrium value V0 by amount of V. Here Pp is nothing but a whole concentration varies into n side. Then the junction it forms, that is of 0. This one. Okay, Pn is equal to Pn of 0. Now the Boltzmann relation for this is P0 is equal to Pn is equal to Pn of 0 e to the power of V0 minus V. I am substituting in this equation. This is of equation number 3. Okay. Now I am erasing all those explanation and I am writing clearly. See, these are all the equation 1, 2 and 3. Now combining equation 2 and equation 3. Equation 2 and equation 3. What we will get? Pn0 e to the power of V0 by Vt is equal to Pn of 0 e to the power of V0 minus V by Vt. Okay. Here Vt is equal to volt equivalent to its temperature. Okay, Vt is not a volt equivalent to its temperature. Now the equation will be Pn of 0 is equal to Pn0 e to the power of V by Vt. Okay, V by Vt. This is of equation number 4. Okay, now the boundary condition is called the law of junction. All these boundary condition, that is nothing but a law of junction. All this is about the depletion layer. Okay, where which law that is to be used in this junction side, all this one. Okay, similarly for electron concentration, till here we discussed about concentration of holes. Now concentration of electrons, let us see. Now the concentration of electrons at p side, that is n p of 0 is equal to n p of 0 e to the power of V by Vt. This is concentration of electrons at p side. This is concentration of holes at n side. Okay, the above equation 4 and 5 indicates the whole concentration Pn of 0 at the junction under forward biased condition. This is thermal equilibrium value Pn0. Okay, this is about concentration of both holes and electrons at n side and p side. Now about diode current equation. From the law of junction we have what we have Pn of 0 is equal to Pn n naught e to the power of V by Vt. This is of equation 1. Diode. Now we are going to discuss about diode current equation, where Pn naught is nothing but hole concentration at the edge of depletion region in n-type material under forward bias condition. By seeing this one only, we have to remember about a forward for biased condition. Don't forget this one, okay? This is a main one. Okay, Pn naught is nothing but a whole concentration of edge of the depletion region in n-type material under open circuit region or open circuit condition. Vt is here nothing but volt equivalent to temperature, where V is nothing but applied voltage. Okay. The difference between the concentration at the junction under biased and unbiased condition is called injected or excess concentration, that is denoted as Pn of 0. I am writing here, let us see. The difference between two concentration at the junction under biased and unbiased condition is called injected or excess concentration. It is denoted as Pn of 0. Here it is nothing but the difference between the two concentration at the junction under biased, this one mainly you have to remember, biased and unbiased condition. Two concentrations at junction under biased and unbiased condition is called injected or excess concentration. Injected or excess concentration. It is denoted as Pn of 0. Okay. Therefore, Pn of 0 is equal to Pn of 0 minus Pn naught. This is of equation number 2. Equation is number 1 we get from the law of junction. Now we are going to find Pn naught. Pn naught is nothing but a difference between the two concentration at the junctions as under biased conditions and unbiased conditions. It is called injected or excess concentration. This Pn of 0. Here it is nothing but Pn of 0 minus Pn naught. The difference between two concentrations under biased and unbiased condition. This is we have to write as equation number 2. Okay. Now using equation 1, now substituting equation 1 in this equation. Using equation 1 and equation 2 in, sorry, not an in, equation 2. Okay. Now Pn of 0 is equal to Pn naught e to the power of V by Vt minus Pn naught. Now I am substituting this equation in this one. Okay. Pn of 0 in this place I am writing this Pn of 0 e to the power of V by Vt. Okay. Now what we will get? Therefore Pn of 0 is equal to Pn naught same. Okay, e to the power of V by Vt, I am taking common out, minus 1. Okay. equation number 3. This is of equation number 3. Okay, ma? Now, similarly, NP of 0 is equal to NP of 0 e to the power of V by Vt minus 1. Equation number 4. It is very easy. See, don't get confused. It is completely about holes concentration and electrons concentration. Okay, where we are here in previously we discussed law of junction where in between depletion region. Now here we discussed about diode current equation by using law of junction. See one by one how it is relation with. Now with a small junction diagram I am going to explain this one. Let us see. This is a depletion region where the whole concentration crossing the junction from P side to N side. Okay, P side to N side, that is given by IPN of 0 is equal to AQ dP Pn of 0 by LP. This is of equation number 5. Similarly, the electron current crossing the junction from N side, this is for P side, this is for N side. INP of 0 that is given by AQ dN NP of 0 by LN. This is equation number 6. Okay, here AQ is nothing but area of cross section of a junction. Okay, area of cross section of a junction. dP is a diffusion constant for holes. dN is a diffusion length for holes. Okay, diffusion constant for electrons. dN is nothing but diffusion constant for electrons. LP is nothing but diffusion length for holes. Ln is nothing but diffusion length for electrons. A is nothing but area cross section of junction. dP means diffusion constant of holes. dN is nothing but diffusion constant for electrons. LP is nothing but diffusion length for holes. Ln is nothing but diffusion length for electrons. Using equation number 3 and equation number 4 in this equation. Now what we have to do? We have to substitute in this equation. Let us see what we will. Now substituting equation 3 and 4 in equation number 5 and 6. Okay. Now the total current I is equal to IPN of 0 plus INP of 0 is equal to we have to substitute in this one. Okay, now IPN is nothing but AQ dP Pn of 0 by LP plus AQ dN NP of 0 by Ln. Okay, now the total current I is equal to AQ dP Pn of 0 by LP plus AQ dN NP of 0 by Ln into e to the power of V by Vt minus 1. Okay. This is our total current I, where all this one is nothing but I naught, isn't it? I is equal to I naught e to the power of V by Vt minus 1. This is equation number 7, where I naught is equal to AQ dP Pn naught by LP plus AQ dN NP naught by Ln. That is reverse saturation current. Okay. For equation 7, it is a required expression. This is a required expression for diode current. This is entirely about diode current. Okay. Without concentration or without considering the carrier generation and recombination in the depletion region. So, if we consider the generation and recombination of the carriers in the depletion region, the general equation of this diode current is approximately given by I is equal to I naught e to the power of V by nu Vt minus 1. Equation number 8. Okay. Where I naught is nothing but a diode reverse saturation current at room temperature. V is nothing but external voltage applied to the diode, where nu is a constant. That is 1 for germanium and 2 for silicon. Okay. Vt is equal to kT by Q. That is nothing but T by 11600. That is volt equivalent of temperature is thermal voltage, where K is a Boltzmann constant. That is nothing but 1.38 into 10 to the power of minus 23 joules per Kelvin. Okay. This is a Boltzmann constant, where Q is a charge of electron. Q is a charge of electron. Okay, Q is nothing but 1.602. Q is equal to 1.602 into 10 to the power of minus 9 C. Okay. T is the temperature of a diode at junction. That is 0 Kelvin. Okay. This is entire about a diode current. Okay. Diode current. Thank you, friends. If you have any doubts regarding this, please comment me on my comment section. Thank you for your watching.